Okay, let us consider scalar particle case at the last time. In the previous class, we have derived the current for the charged scalar particle is IH bar Q over M, phi star round mu minus round mu phi star phi. And it was interpreted to be charge for momentum divided by mass. And if we take the derivative, we find that it is satisfying the continuity equation. And round mu J mu can be calculated directly from this definition. If I take the derivative, I have four terms. Derivative with respect to here, 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 here. There are product of single derivatives. If I take the derivative here and there, I have this term and this term. They are identical, that they cancel exactly. And there are two other contributions. If I take the derivative with respect here and there, I have second order derivatives. But remember that phi and phi star, they are satisfying the same Klein-Gordon equation. These are the results. So from this, I have round squared phi equals minus m squared c squared h bar squared phi. Okay? So for example, phi star round square phi equals, copy this, minus mc m squared c squared h bar squared phi star phi. Okay? And this one, that is just complex conjugate of this equation. So they are the same. So they cancel exactly. Therefore, this current J mu is satisfying the continuity equation. We remember that round mu contravariant form was 1 over c time derivative and minus gradient, but covariant form has the positive sign. So round mu J mu equals 1 over c J0 plus, not minus, divergence J. Okay? So it is satisfying the continuity equation. Why don't we integrate over the space, the whole space? Then left hand side is like that and right hand side. We can make use of divergence theorem over that space, and it is expressed in terms of current times the surface area element of the boundary. If we increase the volume large enough, and if the current decays faster than 1 over r squared, because the surface area is proportional to the r squared of the radius, if it is the case, for example, particle is isolated in some space, then it is true that the charge is moving inside that volume, so the total charge inside is conserved. So partial derivative can be pulled out, and this guy inside, in current J0 integrate over the space can be defined to be that conserved quantity. And that conserved quantity seems to be charged, because if it is real scalar, phi star is the same as a phi, and independent of the introduction of charge Q, it disappears exactly. So for real scalar field, it is charge is vanishing. That's it.